Okay, hello everybody. Welcome to our webinar and also welcome to Tallinn, but virtually. Today we would like to talk about and know about recent advances in impedance source converters. Joining us today are three of the best researchers that have an excellent experience in this field. Let's welcome to Professor Ebrahim Babaei from University of Tabriz, Iran, Dr. Sertac Bayhan from Hamad bin Khalifa University, Qatar, and Dr. Minh-Khai Nguyen from Wayne State University, USA. It's my honor to host you in this event. Let's make a start first with agenda. Today, we will have 4 presentations. Duration of each presentation will be 20 minutes. And at first, we will have a short introduction about impedance source converters. And after that, the first speaker will be dear Ebrahim. He will talk about recent advances in switch Z source networks. The second speaker will be dear Sertac. He will talk about advanced control techniques in impedance source inverters. In the following, I will talk about efficiency improvement techniques for quasi-Z source DC-DC converters. And the last speaker will be Minh-Khai. He will talk about impedance source inverters as an attractive topology. And finally, we will have about 10 or 15 minutes for question and answer. Let's continue with a short introduction about Z-source converters. The story of Z-source converters starts from 2002 as a basic topology was proposed by Professor Peng. The new approach was a solution for to overcome limitations of current source and impedance current source and voltage source converters. It was a practical solution, a 2-level inverter integrated with the impedance source network, and that this topology addressed the shoot-through and short circuit and open circuit issues of the conventional inverter. The converter also is able to boost the input voltage of the input voltage by implementation of the shoot-through states. The novel approach opened a new research field, as now we can see different types of topologies based on impedance networks is proposed, considering input current continuous condition, voltage gain, integration of magnetic elements and number of capacitors and so on. That was also the solution was adapted to all existing types of power converters using different applications such as PV system, wind, power factor correction, and electrical vehicles. The number of publications around these topics and also the attractive topic for research encourage us to overview this type of converters from point of control, topology, and also application. Today, we would like to talk about these converters. And now we can start with first presentation. that present by dear Ebrahim. We are ready to hear from him. Dear Ebrahim, floor is yours. Please start.
Thank you so much, Mr. Hamid. Do you hear me?
Yes, yes.
Hi, everybody. First of all, I would like to express my special thanks for all organizers, especially Dr. Dimitri, Dr. Hamid, and my other friends in Tallinn University of Technology for inviting me as one of presenter for this great program. Also, I'm so happy to visit my old friends in this session. The title of my presentation is Recent Advances in Switch-Set Source Networks. As you know, there are so many different topologies of impedance source converters. In this presentation, I will focus on switch-Z source networks, and I will try to classify the different topologies of switch-Z source networks. And also, I will present general circuits to generate different topologies. And moreover, the operation and analysis of all topologies are briefly given. And finally, the design consideration will be given for all topologies to show the advantages and disadvantages of different topologies by numerical examples. Due to the limited time, I ignore some slides about introducing Z source topologies because all participants are familiar with the basic operation of the Z source converter. Okay. In this slide, I classified the switch Z source network in general form. Generally, we can divide the switch Z source networks to basic switch Z source networks and high boost switch Z source network, as shown in this figure. In this figure, for each group of switch Z source network, there are different subgroups as shown. So, according to this figure, there are more than 40 different switch Z source network structures that in the next slide, all of them are presented and analyzed separately. In this slide, here, one main group of switch Z source network is shown by basic switch Z source network. In this slide, just the classification of basic switch Z source network is shown. According to this figure, the conventional basic switch Z source network is divided into three different topology, namely switch boost network and embedded SVN. Series SVN is divided connection, and its topology is divided into types 1 and 2. The power circuit of the conventional basic switch Z source network is in general form is shown in this figure. In this figure, there are 4 places to apply the voltage source, and there is only one of them is used, and the other 3 voltage sources can be replaced as short circuit. Due to inrush current problem, the voltage source will not be able to connect in series with capacitor C in block 4 and in block 5, and also with switches with switch SC or SE. And also to increase the voltage boost factor of the converter, the voltage source will not be in series with diode DB here or DB here. This means there is no series connection between voltage source and blocks 2, 4, and 5 in this figure. Also, there are 5 blocks with yellow background color in this figure that each of them has two components. Based on the type of the basic Z-source network, one of these elements will be used in the indicated place. As mentioned before, the possibility of connecting input voltage from 4 different points to the switch Z-source network, generally without considering the place of voltage source, the conventional basic switch Z-source network has 2 types of 1 and 2. This table shows how the components of the basic switch Z-source network should be placed to form 2 different kinds of network. It is important to note that the location of the passive components, the location of passive components are same, and just the location of voltage sources is different. For example, in type 1, from block 1, we have choose the diode. From block 2, so here from block 2, we have choose S3, and from block 3, we choose L, and so on. So the position of passive components are exactly same for each type. Just the location of the voltage source is different from one topology to another topology. For example, in type 1, in the first type, the capacitor C is connected to the negative pole of the DC link, as shown by I'm showing by mouse, and the collector of switch is connected to positive polarity of capacitor. While in the second type structures, in all structures of the second type, the capacitor C is connected to positive pole of the DC link, and the collector and the emitter of switch is connected to negative polarity of capacitor. Despite these differences, the relationship between the voltage across the elements and current flow of them do not differ from type 1 and 2. Here we have shown 8 different topologies for the first basic structure. These different topologies have been presented in different references. In all of the shown structures for the conventional basic switch Z-source network, in normal condition, when the DC link is short slow, this means the converter is operating a short slow operation. The switch, the power switch is turned on, and both diodes DA and DB are turned off. And in the non-short slow operation, the switch is turned off, and the diodes DA and DB turned on. In these figures, I have shown their equivalent circuit for both operation of short slow and non-short slow operation. By applying KVL and KCL and considering basic laws such as voltage balance law and for inductors, we can obtain the voltage and current of all elements for both operation of Schuster and non-Schuster for all three basic units. Here, VSC means, for example, VSC is the average voltage across the capacitor. VI is the value of input voltage, and IL is the console, the inductor. By using the previous slide, we can calculate the boost factor, the voltage boost factor for different topologies, and all of these boost factors are shown by these equations. This figure shows the variation of voltage boost factor versus Schuster duty cycle. According to this figure, for the same values of duty cycles, Schuster duty cycle, the invented switch boost network can generate more voltage boost factor in comparison with switch boost network, conventional switch boost network, and series switch boost network. This figure, the left figure, shows the voltage across across the capacitors based on the ST duty cycle, Schuster duty cycle. It can be seen that although voltage boost factor for switch Z source network SPN and series SPN are the same as shown here, but the voltage space of series SPN is less than other topologies. In addition, it is clear that the voltage stress across the capacitors, in embedded SPN is higher than to other structures. In the middle and left figures, here, this figure shows the voltage stress across the power switch, and this is for total voltage stress diodes. It is clear that the voltage stress across the power switch and diode in embedded switch boost network is more than SPN and series SPN. The general power circuit of the dual topologies of the basic switch Z source network, the structure is shown in this figure. In the previous slide, we have used voltage source based topologies. Here we talk about the current source based Z source topology. Like the conventional basic switch Z source network converters, there are two types of switch Z source network for its structure, type 1 and type 2. There are three places to apply the current source, and there is only one of them available in every situation, and the other two current sources should be considered as open circuit. Due to increase in current boost factor of the converter, the current source cannot be arranged in parallel with DB, diode DB here, and switch S. And also due to high voltage stress, the current source will not be in parallel with inductors. The placement of elements to create the dual topologies of switch Z source network structure from general power circuit is shown in this table. Here, again, we list 6 different topologies for dual basic switch Z source network. Some of them are presented in these references. The relationship between voltage and current for all topologies all shown in this table. Here, IL means the average current of the inductor, IR the value of input input current. The value of current boost factor for each of these structures is calculated by this equation. According to this equation, the current boost factor for dual switch Z source network and dual series switch Z source network is same. Here, this figure shows the variation of current boost factor versus Schuster duty cycle. According to this figure, for the same value of Schuster duty cycle, the dual embedded SPN can generate more current boost factor in comparison with dual SPN and dual series SPN. This figure shows the current hysteresis of the inductors based on the ST duty cycle. It can be seen that although the current boost factor for dual switch Z, dual SPN and dual series SPN are exactly the same, but the current hysteresis of dual series, switch Z source network is lower than less than dual switch Z source network structure. In the middle and the right figure, we have shown the current stress on switches and also current stress for total diodes. Again, remember the general classification of the switch Z source network topologies. Until now, we had a discussion about basic switch Z source network, this part, the topologies highlighted by yellow background color. Now we are going to have discussion about our second group of switch Z source network structure, namely high boost switch Z source network. In this slide, just the classification of high boost switch Z source network is shown. The general power circuit of couple, one of the, as shown in previous slide, as shown here, one of the main group of this, one of main group of high boost factor topology is called coupled switch Z source network. The general power circuit of coupled switch Z source network structure is shown in this figure. According to this figure, it is clear that there are 4 blocks for arranging inductors, that only 2 of them are selected in its structure, and 2 other blocks will be short circuit. For example, if we choose 1 and 2, the inductors shown in blocks 3 and 4 should be replaced by short circuit. There are 4 different topologies for coupled switch Z source network, as shown in this table. The method to select the blocks to constant different coupled switch Z source network structure from general power circuit shown in this table. According to this table, it is clear that all coupled switch Z source network structure have the same number of components. The components are exactly the same, but the location of coupled inductor is different from one topology to another topology. Also, it is important to note for the comparison different topology, the turns ratio of coupled inductor for all structures shown in per unit by n by n over 1. Also, it is important to note that it is possible to generate two more structure for coupled inductor switch source converter by using this general topology. But this topology do not have the capability of boost factor, hence they are not included in this table. Consider here by using these different positions of coupled inductor, it is possible to generate 6 different topologies, but 2 of them is not acceptable because of not acceptable because not able to generate acceptable boost factor. These topologies has been presented in these references. The average voltage, excess capacitor, and boost factors are for all structures are shown in this slide. In this figure, the top figure shows the maximum value of the duty cycle, this value, according to the value of N. N is the turns ratio of the coupled inductor in types, for types A, C, and D. Here, the bottom figure, this figure shows the maximum value of duty cycle, Schuster duty cycle, according to the value of N for type B. It is clear from these two figures that the maximum value of duty cycle in different values for N for type A, B, and AB is equal to 0.5. While according to value of N, it can be selected to close to 1 for type C, 1 for type C and D, the blue color. Also, it is important to note here, I should to be mentioned that the value of the duty cycle is valuable based on the switching method and the modulation index. This figure shows, this figure compares the voltage boost factor of coupled switch net source network structure for 4 different types of N. Here for different types of N, and for example, equal to 0.5, 2, or 4. We compare the boost factor for different topologies. It can be seen that by increasing N, leads to decreasing the length of duty cycle in type A, B, and D. But this is reverse in type C. Also, this means by increasing the value of N, the types A, B, and D leads to higher boost factor in smaller values of Schuster duty cycle. Another type of this group, high boost switch net source network, is diode assisted switch net source network. In these two references, 2 types of diode assisted structure for switch net source networks have been presented. The power circuit of this structure are shown in this slide. According to these figures, both of the structure have two inductors, 2 capacitors, 4 diodes, and 1 switch in Z source network. The voltage boost factor of these topologies are calculated from the given equation. For this is for this topology, and this one is for this topology. Another kind of switch high boost switch Z source capacitor is switch capacitor switch Z source network. In this reference, the Swiss capacitor or quasi-Z source boost network has been presented in two types. According to these figures, the Swiss capacitor topology have been combined from one inductor, two capacitors, three diodes, and one switch. The diodes DA and DAB are inverse bias in Schuster operation mode, and the diode D1 is in forward bias. Also in non-Schuster operating modes, the diodes DA and DAB are in forward bias, and the diode D1 is in reverse bias. The boost factor for this topology is given by this equation for both topologies. And another subgroup of high boost switch Z source network is switch inductor switch Z source network. This topology is divided into four main groups, and each group consists of two types, type I and type 2. This figure shows the general power circuit of switch inductor switch Z source network to generate different types of switch Z source network. The structure of the switch Z source network include two inductors. All of here we have used SL1 or SL2. These cells are shown by this topology, consists of two inductors and three diodes. In general form, these types of topology have higher voltage boost factor in comparison with conventional structure-based switch Z source network, but they have many components in their Z source network. By changing the connection of Z source network in switch Z source in switch inductor topologies, different structures similar to basic switch Z source network are obtained. Here, in this figure, in this table, 8 different topologies have been presented for this type of topologies. It is important to note the number of elements are the same in all of them. For all of them, the number of components are exactly the same. And different structures are created by different connection between components of Z source network and position of voltage source. By choosing different position for voltage source and choosing different component from this block, we can generate different topologies. Here we have shown 8 number of them. These topologies has been presented in different journal papers. Some as I have shown some of them. The voltage and current equation of the switch inductor structures in two Schuster and non-Schuster operating modes are shown in this table. It is important to note that these equations are similar for type 1 and type 2 structures. In this equation, we have used VL2. The value of this equation are given by this equation, and the VSC is the average voltage across the capacitor. VI is the value of the input voltage source. And also the boost factor of all topologies, different topologies are given by this equation. For example, here we see that for 2 of them, the boost factor for of them is exactly same, but for the rest of topology are different. Another type of switch Z-source network is modified switch Z-source network. Here, usually we use less number of diode to generate high boost factor. Here, this structure consists of two inductors. All of these are consist of two inductors, two capacitors, two diodes, and one switch. Just the position of the component are different from one topology to another topology. The top figures, in these figures, we have discontinuous input count, but for bottom figures, for bottom topologies, we have continuous input count. This is the difference topologies, the difference between these topologies. Also, the boost factor for this topology are given by this equation. Again, these topologies are presented in these references. In this table shows the equations of voltage and counting ST for ST and non-ST. This is for ST and this is for non-ST operating modes for modified switch Z-source network structure. Also, the limitation of duty circuits determined for all topologies for different operation modes. This figure shows the variation of the voltage boost factor for switch inductor topologies. According to this figure, the diode assisted here, this one, the diode assisted switch Z-source network has a higher boost factor in comparison with other structures. Also, in low values of duty cycle, the voltage boost factor of coupled switch topology is more than other topologies. This table shows the number of elements in different types of high boost switch Z-source structures. In here, we also show the average voltage across the capacitors, also the voltage boost factor for different topologies. Here we compare different topology from number of components point of view. Here, to compare different topologies, we have designed different topologies, so many topologies by numerical example. Here we consider boost factor equal to 5. Here, B equal to 5, and also the input parameters. In this case study, the input voltage is assumed 35 volts. The switching frequency is assumed 20 kilohertz, and the value of load is assumed 75 ohms. For this condition, we designed all topologies. Here, the values of the passive elements with their voltage and current rate are calculated. For all passive components, we have calculated the stress voltage across capacitors. Also the stress count of the components to compare different topologies. I have highlighted So because there are so many numerical result here. In this table, some results are for comparison. According to this column, the minimum count rate for semiconductor elements is needed for embedded, for this one, embedded switch boost network. This means for the same condition, for the same boost factor, minimum count for semiconductor devices will happen is happen for embedded switch boost embedded switch boost network. For another example, the maximum diode count here is needed for DC link modified switch Z source network, and the maximum switch count is needed for diode assistance switch Z source network here. And the minimum switch voltage is for DC link is for DC link is for modified switch Z source network. Because we have a limited time, for more information, please see this reference. In this reference, you can find more details about analyzing the different topologies of switch Z source network. Also, you can find design consideration for different topologies of switch Z source network, and you can find different application for switch Z source network. Thank you so much for attention. Sorry, do you hear me?
Yes, dear
Yes.
Ebrahim, thank you very much for your nice presentation. Could you please unshare your screen? Okay, thank you very much for your nice presentation.
Thank you, Mr. Ahmed. Thank you.
Now, because we consider the time, it's time for Sertac to start his presentation. Dear Sertac, hear me?
Yeah, I can hear you. Thank you.
Thank you. Please start.
And first of all, thanks for inviting me to give this short presentation. And hello, everyone, and greetings from Qatar. I would like to also take this opportunity to hope all you are okay and staying safe, especially during this unusual time. In this presentation today, I am going to talk about some of the advanced control techniques we have implemented for impedance-source inverters. I'm not going to give more details because we have limited time. This is the agenda of my speech. I will start with the introduction, very fast introduction for the traditional quasi-source inverter, and then I will present model predictive control, case studies, sliding mode control, and case studies. And as you can see in this slide, typical single-stage PV inverters. And as you know, photovoltaic cells voltage varies widely with temperature and irradiation, but the traditional voltage source inverter cannot deal with this wide range of range without overrating of the inverter. The input DC voltage must be greater than the peak AC output voltage because of the voltage source inverter operates as a buck converter. And you know, we need also the controlled output. Since we have limited voltage range, it is better to introduce some let's say solutions to solve this issue. First of all, to overcome this issue, some topologies have been proposed. As a first solution, maybe the simplest way, a transformer can be used between voltage source inverter and grid to cope with the range of the PV voltage. The main advantage of this topology is that it is easy to implement and no need extra control circuits. On the other hand, adding transformer in the system results in increase in volume, cost, and of course, it will reduce the efficiency of the system. And the second option can be adding a boost converter in the system, as you can see here. And this is the one of the most used topology actually in the PV systems. This solution also comes with the range of PV voltage, and maximum power point tracking is relatively easy. However, this leads to a higher component count, especially in terms of the active components, active switches. And sometimes control structure is complex. Of course, when we are introducing new active switches, cost will be higher. As my colleague previous slide, they presented in the previous slide, to overcome these issues, in beginning of 2000s, the impedance-source inverters presented. Impedance-source inverter presents a single-stage structure to achieve the voltage boost buck character in a single power conversion stage. And this topology has been widely used in PV applications, especially in the academia. And this type of converter can handle the PV DC voltage variation over a wide range without overrating the inverter. As a result, the active component count and the system cost can be reduced with, of course, the improved reliability due to a low short-through state. And in the impedance source network, basically we can use either Z-source network or quasi-source network. As I mentioned, it will bring high reliability because when we introduce impedance source network in the converter topology, we can, in case of any short circuits, still we have capability to continue, and the system efficiency is higher than the other presented topology. Of course, there is no any active switches between the DC and DC link, so it will bring also some cost reduction. Now, of course, now we need to talk about the control. The control of impedance source converter plays critical role to ensure the system stability. Because we have single stage topology, we need to control DC side and as well as the AC side. And in the literature, a lot of feedback control methods for shoot-through the cycle were proposed in order to stabilize the DC link voltage of the impedance source converters as well as the output currents. As you can see here, traditionally single loop control or double loop control, we will see later, we can use easily PI controller. As you can see here, we can easily use the PI controller. Here, input voltage, DC source voltage, I mean the input voltage, capacitor voltage, or measured or calculated VPN, which is the DC link voltage, which is compared with their references to obtain the common signal through a voltage source controller. Actually, as I told you, in a basic way, we can use proportional integral PI regulator. And the common signal is shoot-through dirty ratio. The output of this one is the shoot-through dirty ratio. And it can be another inner current loop. Here we are controlling the voltage, which is single loop control. But if we want to also include the current loop, we are calling it double loop control. So it can, when we introduce this inner current loop, it can increase the stability margin of the inverter. Okay. And please note that right now the single loop control or double loop control, I am talking about only the DC side control, and it is related to shoot through that cycle. Okay. And here I just give two examples for the overall control structure for the Z source and quasi source. And as you can see here, in order to control the whole system, we need to introduce several PI regulators for the AC side and also for the boost control. Boost control means there is single loop or double loop control inside. Okay. Here it's more clear. There is single loop control, and this part is for the AC side control. I mean the output current control. This is the traditional way we can control impedance source converters. Now the first advanced control technique I am going to present here is model predictive control. Of course, I'm not able to present all details of the model predictive control due to the time limit. I'm just going to present here the main idea of the model predictive control. After that, I will present some case studies. And in this figure, you can see the main block diagram of predictive control. And the main characteristic of predictive control is to use model of the system for predicting the future behavior of the controlled variables. And this information, I mean, the output of the predictive model is used by the cost function in order to obtain the optimal switching states for the converter. This converter can be 2-level, 3-level, or any converter topology. Okay, this is very general block diagram for the model predictive control. And here in this figure, we can see the working principle of model predictive control. The future values of the states of the system are predicted until a predefined horizon in time. In this figure, for example, it is K plus M, and K plus M using the system model and the available information. What is the available information? I mean the measurements. For example, it can be current measurements or voltage measurements until time K, okay? The sequence of optimal actuation is calculated by the minimization of the cost function, and the first element of the sequence is applied. This whole process we will see in the flowchart in the one of the case study. This whole process is repeated again and again for each sampling instance, considering the new measured data. Okay, so you can see this is our set point, and this is our let's say the system behavior, and we can track the reference easily through model predictive control. One of the main advantage of model predictive control or predictive control is concepts are very simple and intuitive, and using predictive control, it is possible to avoid the cascaded structure. What we see here, there are a lot of PI controllers and there are cascaded structure. And by using the model predictive control, we can avoid the cascaded structure, actually, which is typically used in linear controls techniques. And we can obtain very fast transit responses. We can see in the results very soon. And this is the just basic concepts. I don't want to read all. And you can more information you can find in this chapter. Here I would like to share one case study. It was published in Industrial Electronics, Transactions on Industrial Electronics, Model Predictive Control for 4-leg quasi-source inverter. You can see the structure of the circuits here. As an input, we have the quasi-source network, we have 4-leg inverter, LC filter, and of course, unknown loads. This is the system parameters. And this is the control structure. As I told you, the model predictive control is very easy, and the structure, the control diagram, you can see it is almost the same what I presented in the general block diagram. We need, of course, some measurements for the prediction of the variable, and also we need to create cost function in order to find the actual the possible the optimum switching states for the inverter. Of course, we also need references. Now let me go step by step in the flowchart. For example, you can see this model predictive control and the predictive models need to repeat for every sampling time in the for loop. In the for loop, you can see we have 16 actually states. 17 states. 16 states for the 4-leg inverter. 2 to 4 is 16 switching states. In the non-shoot-through states, And we have also one additional state, which is a shoot-through state. So I have 17 switching states for this control system. And I have also three prediction model 1, model 2, and model 3. Why I have three model? If you look at here, my control variable is, first of all, the output current, okay, and the input current, and the DC link voltage, okay. I'm going to control this VC1, so I am going to actually control the VPN. So the first, you can see the predicted model output voltage and the output currents. Because this is standalone system, I want to keep the voltage constant, okay. So I'm not going to, of course, go over this mathematical equation, so we don't have time. This is from the mathematical model of the system, okay. The second model for the inductor current, I mean the input current. And when we focus on the predictive model 2 and predictive model 3, we need to consider also shoot-through and non-shoot-through, okay? Because the model of the system depends on the switching states. First of all, I need to determine if the state is shoot-through or no. How I can define it is very easy. As I told you, I have 17 switching states. So I have 16 non-shoot-through state and one shoot-through state. In here, in the counter, if I reach the 17, it means that, okay, this is shoot-through state. I need to use this equation, okay, to calculate the inductor current. Similar things for the model 3. In the predictive model 3, I am controlling the capacitor voltage. And the same condition is here, whether it is shoot-through or non-shoot-through, okay. I can define easily because I know how many switching states I have. And this is the predictive models. Since I have three control variables, I need to write three models. In the next step, I need to also write the cost functions. Since I have three control objectives, I need to write three cost functions accordingly. The first one is for the output voltage, the second one for the inductor current, and the third one is the capacitor voltage. Of course, this three, I need to introduce single cost function. How I can introduce single cost function? With some weighting factor, okay. And this is the critical point of the model predictive control, because this in this example, since I am controlling three variables, I need to introduce weighting factors, okay. And how we select the weighting factor, actually the weighting factor selection is still an open topic for research. Right now, there are no analytical or numerical methods to adjust weighting factor. How we decided, we defined three performance criteria. The first one is the output current error, input current error, and the capacitor error. And we repeated hundreds of simulation, actually, starting from 0 to 1, and we found this area gives us the optimum performance area, and we selected weighting factor 0.75. I mean the delta lambda I, sorry. And we multiply this one 0.1 to find the lambda V. So for the lambda, this one is the 1, because this is the highest part, 1. And this one we selected 0.75, and this one is 0.075. Let's look at the example results. I didn't put all the results here. If you want to see more results, you can just go this paper and you can find more results. These two examples are for the steady state results. As you can see, the output voltage is constant, and in this example, I think our output load is 10 ohm, and the output voltage reference is 110 volts. And as you can see, there is no any neutral current since load is balanced. And the DC link side, you can see the VPN, VC1, VC2, and IL1. And when we introduce the, for example, in the second case, we change the load for each phase. The phase 1 is the 30 ohm, phase 2 is the 10 ohm, and phase 3, 6 ohm. And you can see also we introduce inductive characteristic load for the phase B and phase C. So each phase has different loads, and you can easily see, since it is 4-leg inverter, there is neutral current. In case of unbalanced load condition, even the controller handle the situation, and you can see the current is sine wave, the harmonic distortion is within the boundary, and also there is no any distortion on the DC side. And also you can look at the dynamic response of the system. At this point, we are actually increasing loads from 30 ohm to 15 ohm, almost 100% increase. And you can see the system response is very fast, DC, AC side and DC side as well. This is, of course, the balanced load condition. And unbalanced load condition, you can see again the initial condition was 15 ohm per phase. And then we are keeping the first phase A 15 ohm, but first phase B 30 ohm and phase C 22.5 ohm. And you can see the response of the system. Again, it's very fast. And look at the output voltage is constant, okay? Because we are also controlling the output voltage. Again, this is just, I selected two for the state and for two transit response. You can find more results in this paper. And this is the example for the model predictive control. Another control technique we are using in our actually research, sliding mode control. Sliding mode control is a non-linear control method. It alters the dynamics of non-linear system by application of a discontinuous control signal that forces the system to slide along across a section of the system normal behavior. The idea behind sliding mode control is to choose a sliding surface. Okay, this is the sliding surface you can see here, along which the system can slide to its desired final value, which is here. And this figure gives a graphical representation of the trajectory of a system under sliding mode control. The entire sliding mode operation can be divided into two phases. In the first phase, we are calling it reaching mode. You can see here. Actually, it is regardless of the initial position of the control trajectory. Okay, it can be here or here. Okay, it doesn't matter. So the sliding mode control will force the trajectory toward the sliding surface. Okay, the sliding mode control will force this point toward the sliding surface here. When the trajectory touches the sliding surface, the system enters the second phase. Okay, and we are calling it as a sliding mode. Okay, the second phase we are calling it sliding mode. And in the second phase of the control process, and we can also say to be in sliding mode operation, the system will then be controlled by a series of infinite switching of its control functions. As you can see, the trajectory is maintained on the sliding surface and is concurrently directed toward the desired equilibrium point O, and finally setting at O. Okay. Importantly, by having a control process that reacts only the way the trajectory behaves, the trajectory will be immune the effects of parametric changes and external disturbances as well. In other words, the control process utilizes the sliding surface as a reference path. Okay, and when the control trajectory will track actually eventually to the origin to achieve steady state operation without any consideration of the system's parameters and operation conditions. We'll see in the case studies. And unfortunately, we do not have time to focus on more on the sliding mode control. But there is another webinar on, I think, if I am wrong, Andre, please correct me, on 6th of April. There will be another webinar on advanced control techniques for power electronics converter, and my colleague Hasan Kömürcigil he's going to present sliding mode control for power electronic converters. And I think he will give more details about it because I don't have time right now. I need to show you maybe in the case study, it will be more clear. Now you can see another quasi-source inverter topology. We actually recently used a lot. Quasi-source T-type inverter. And if you notice one thing, this is three-phase system, but we use only the two-leg, okay? And the third phase is connected to the middle point of the capacitor. And I'm not going to repeat all this shoot-through state of the system. You can just refer to this paper recently published in ICON 2020. And this is the system and control parameters. The important thing is this study, we controlled AC side and DC side through sliding mode control. Okay, we use two different sliding control functions to control the DC side quantities and as well as the AC side quantities. That's why we have two sliding coefficient, which is alpha, which is 1.4. The second one sliding coefficient is lambda, which is 9,000. Okay. Let's start with the control of quasi-source network. I mean the DC quantities. Okay. And we have 8 variables for capacitor voltage and for inductor currents. The nature of the topology VC1 and VC4 is actually identical, is equal. VC1 and VC4 and VC2 and VC3, they are equal each other. And all the inductor currents are equal as well. So it is sufficient to control VC1 and VC4 and IL1 only. Okay. So this is the sliding surface function. We selected state variables. The first one is the capacitor voltage, and the second state variables is the inductor current. And the first state variable, you can see here, the error between the VC1 minus VC1 prime. This is the reference value of the VC1, which is, I believe that 200 volt in this study. And this is also VC1 minus the reference of the VC4. And the second state, state is the inductor current, and it is also IL1 minus the reference of IL1. Okay, this is both are error variables. So I can calculate the reference inductor current in two ways. You can see here from the model of the system. The first one, the first equation, I need to know the. Let me just go here. I need to know the Ri, which is the first, let's say, first inductance resistance value, and also I need to know the Ro. Okay, it depends on this two variable, and of course I need two measurements as well. And you can see when I use this one, it will be actually parameter dependent. Directly parameter dependent. If the inductance resistance change, this will give me wrong assumption or wrong reference value. But on the other hand, if you look at this one, this is also the same. But here I do not have any dependency on the parameter. But here I need to measurements will be one more. The output of the first sliding mode function will be my actually will be my duty cycle ratio, and this is the switching scheme of the controller. This is for AC side control, I mean, and this is for the impedance source network for the show through. And the second sliding mode control, I mean, in this still we are in the same control. We need to write another function for the AC side. And in AC side, if you remember, we have only 2 voltage to control. Since we do not have the third phase, okay, third leg, let's say, we have third phase, but we have only 2 leg. So we have to control the 2 variable, which is VCA and VCB, okay? So we have 2 variable. And this is the actually guarantees the existing of sliding mode. If the sliding function multiplied by the derivative of sliding function is lower than the 0, it means that my controller is stable. Okay. Of course, for example, in AC side, you saw we have a CL filter. The resonance can be also problem. Okay. But in this study, we didn't use any damping method, okay? Just for the controlling the output current. And although the system remains stable in the sliding mode, the chattering occurs. What is chattering? The term chattering describes the phenomena of finite frequency, finite amplitude oscillation. You can see here appearing in many sliding mode implementations. This is actually main drawbacks of the sliding mode control. These oscillations are caused by the high frequency switching of the sliding mode controller, which results in switching frequency actually oscillations. The effects of chattering can be reduced if the discontinuous switching action is replaced with a hysteresis function. It's also possible to reduce the chattering by smoothing the discontinuity into sliding surface function. For example, in this study, we use smoothing technique, and we use some boundary layer phi, okay? And the switching, actually this chattering was within this limit. How we did this one? This is the, you can see sliding mode function, and just dividing by this, I think it was 1000. Yes, boundary layer thickness is 1000, and it gives us almost constant switching frequency. Let me present the results. And you can see here in the figure 4 is the steady state results. Figure 5 is the dynamic response. In the look at the steady state results, our VC4 and VC1, as I told you, reference value is 200. And you can see the reference value, the actual value tracks the reference value. Also, you can see the IL1 reference and the IL1 actual. The actual one tracks the reference satisfactory, they have with high accuracy, and you can see the voltage levels and the output currents. And you can see this is the actually the current is multiplied by 10. And you can see the current and the voltage in the same phase. So I have two sliding functions. One is controlling the DC side quantities. The other one is controlling the AC side quantities. If you look at the dynamic response, as you can see here, really on the right-hand side, we increase the current, okay, current reference. I mean the reference here from I think it was 13 to 20 amp. So you can see here the actual value tracks the reference value in maybe 0.2 seconds, and there is no any distortion on the DC voltage side. And you can see here also AC side there is some overshoot, but still it's acceptable. I think it is less than 0.2 0.1 seconds. Yeah. And another study, sliding mode control. Here you can see in this study we used quasi-source neutral point clamped inverter single phase. In the study, I just want to mention DC side quantities we used the PI based controller. AC side quantities we used sliding mode control. Okay, you can see the sliding mode control. Actually, it is very easy. I also prepared. Let me just, if I can switch here. I think this one. Yeah, this one exactly. MATLAB Simulink representation of the sliding mode control. Here we have the PR control. This is for the damping since we have the LCL filter. And this part is, you can see, very, very simple. we have the alpha. I will go back to presentation. We have the alpha, you can see here, and we have the derivative function, and we have the thickness boundary in order to reduce the chattering effect. And of course, we have the PR controller, proportional resonant controller, in order to damp the resonance effect of the because of the SEL filter. You can see the sliding mode control is very easy, and here also you can see the results. Because as I told you, we used a sliding mode control for only AC side. This is the voltage and this is the current waveform. Okay. We go again here. Here there is some results, experimental results, because we also published this one. I think it was in IEEE Access. You can also read more. I think I do not have time. I need to go to the conclusion. Unfortunately, we don't have time to present all the, let's say, control structures in a very short time. I just focus on the model predictive control and the sliding mode control. And as I mentioned, model predictive control structure has many advantages. The main advantage is very simple to implement it, and you can include many cost function, many control objective in a cost function, but it has some disadvantages as well. Larger number of calculations needed if you compare to the classical controllers. And the quality of the model have direct influence of the quality of the resulting controller. So it is model dependent. Sometimes it doesn't give good results in case of very, let's say, large change in the filter parameter. Sliding mode control structure has also several important advantages. Actually, sliding mode control is naturally well suited for the control of variable structure system. It offers excellent large signal handling capability, which is important for DC-DC converters. And by replacing linear pulse width modulation controllers with sliding mode controller, power converters can achieve better regulation and dynamical performance for wider operating range. And the main drawbacks of the sliding mode control, the switching function, and may cause chattering in the control variable. Of course, there are many techniques to reduce the impact of the chattering. It was the last slide. And thank you for your attention. I believe that we are receiving the questions at the end of the session. Thank you. Thank you so much.
Thank you very much for your nice presentation, dear Sertac. Yes, we will back you at the end if there is some questions. Now we have time limitations. Let's start my presentation. Oh. Okay. Okay, I would like to present my presentation entitled of Efficiency Improvement Techniques for quasi-Z source DC-DC converters. My presentation includes a short introduction about module level power electronic system as a solution for power systems, and I will continue with the photovoltaic converter as a practical solution for these systems. And in the following, I will continue with the DC-DC part of this converter and efficiency improvement techniques for that. and finally, it will be ended by some discussion and conclusions. As you know, replacing fossil fuel energy with renewable energy has grown exponentially recently. Between different renewable energy generation technologies, solar PV technology is a superior solution, especially for residential residential renewable energy generation.
Hamed, this is Andre. Excuse me for interruption, but nobody can see your slides.
Can?
Yeah, you share only the folder. You make sure you share all the window or the particular window for that.
Sorry. Now, can you see?
Now, yes.
Sorry, let's start from beginning. Sorry. My presentation includes a short introduction about module level power electronic systems, and in the following I will continue with photovoltaic optoinverter as a practical solution for these systems, and after that I will focus on DC-DC part of this converter and efficiency of this converter and some techniques for improvement of this efficiency. Sorry. Okay. As you know, replacing fossil fuel generation energy with renewable energy generation has grown exponentially recently. Between different renewable energy generation technologies, solar PV technology is a superior solution, especially for residential renewable energy generation systems. As according to the statistics, about 6% of renewable energy generation technology belongs to solar PV. It shows that it's essential to maximize the utilization of PV systems with an efficient processing of electrical power. In order to achieve this aim, we need an interface to relieve the issues about PV systems, such as partial and opaque shading issues and compatibility and mismatching issues. Module level power electronic system is a practical solution for these issues. We can use these systems to don't let operation point of shaded panels effects on operation point of unshaded panels. Module level power electronic system should have a implementation of maximum power point tracking and GMPPT, also compatibility with PV modules, and having a flat efficiency curve in a wide power range. Different kind of module level power electronic systems is proposed. Between them, one is photovoltaic optoinverter that is proposed, produced, and presented by Ubik Solution Company, not as a concept, but as an industrial level production. This optoinverter is a first hybrid of PV power optimizer and PV microinverter. That means a novel approach combines the key advantages of photovoltaic power optimizers and also microinverter. It, as a power optimizer, it features the best shade tolerance and energy yield without power clipping. And as a microinverter, features a PV system design flexibility, safety, and also direct AC connectivity. Here you can see main aspects of this optiverter are listed here. Some of them is the wide input voltage range between 8 to 60 volt, and also compatibility with the available 60 and 72 cell PV modules, and having a SEC efficiency of 95%. The power circuit of this converter includes 4 main parts. DC-DC part is used for issues about the partial shading and shade tolerant, and also isolation transformer that provides galvanic isolation and step up the DC-DC, step up the input voltage. We have a grid tie inverter at the output. It utilizes a simple H bridge. The output of the DC-DC converter linked to input of grid tied inverter by high voltage DC links capacitor that filters the output voltage of the DC-DC converter. An LCL output filter is used to reduce the switching noises and also create the sinusoidal output waveforms. As it mentioned in this presentation, I will focus on DC-DC part of this converter and efficiency improvement techniques for that. This DC-DC part of this converter is a quasi-Z source based isolated buck boost converter. The circuit of this converter includes a quasi-Z source network along with H bridge inverter. There is an output voltage doubler rectifier at the output side, and an isolation transformer is used to provide the galvanic isolation and also increase the input side voltage. The leakage inductance of transformer along with the capacitor of voltage doubler rectifier consists a resonance tank. The converter operates in 2 mode, boost and buck mode. For buck boost mode, the quasi-Z source network is active, and also the series resonance converter that switch of inverter controlled by shoot-through PWM techniques. But in buck mode, the quasi-Z source network operates as an input filter and is disactive, and we have only series resonance converter that the switches of inverter are controlled by phase shift modulation. The boundary between modes is determined by spatial value of the input voltage, and in this point, the converter and switch of inverter are controlled by PWM without implementation of shoot-through states. But this point is called as an pass-through operation mode or normal mode for a spatial value of the input voltage. The converter features ultra input voltage range, and also thanks to quasi-Z source network, it has a continuous input current, low inrush current during startup, low input current rip, and also lower power loss in the input side. The converter features a high efficiency at full load conditions. Here we focus on efficiency of the converter, but not in full load condition, but in low light and part load condition, because the converter suffer from low efficiency at part and light load conditions, and it is need to pay more attention to part and light load efficiency of the converter. The question is why? There are some reasons for that, but One of them is the location of the place that PV system is used. As you know, in northern latitudes, as can be seen from the figures, the irradiation level and also potentiality of the photovoltaic power is low. In this condition, if the converter operates in low efficiency, and because the system is in low power, the annual energy of the system will be low, and it is need to improve the curve of the efficiency for the during this year to improve the efficiency and also efficient system. In order to improve the efficiency, we should know which parameter affects on light load efficiency. Analyzing the power losses of the converter and loss sources shows that switching losses dominate over the other loss sources of the converter at part and light load conditions. Then we need to decrease the switching losses. For that, we have two solutions. One is frequency reduction techniques, and the other is cycle skipping modulation. Because of the limitation of time, I don't go to the detail and also present result of analysis. Implementation of the techniques shows that for switching frequency reduction techniques, switching losses is decreased by decreasing of frequency, but there is some shortcoming, such as increasing of current ripple in causes Z source, couple inductors at the input side, also increasing the ripple of magnetizing current of transformer, and also flux density swing of the transformer is increased. In case of cycle skipping modulation, this technique has a good effect on reduction of switching losses, and it reduces the switching losses, but current ripples in couple inductors and also magnetizing inductance is increased, but the effect of cycle skipping modulation on core losses and core flux density is comparing with frequency reduction is low, and it has smaller effect on core flux density. In order to verify the analysis, you can see here the result of power loss distribution and also the efficiency of the converter. As can be seen, by reduction of frequency, the switching losses decrease, and also implementation of cycle skipping modulation has a good effect on reduction of switching losses. But the effect of cycle skipping modulation on efficiency for light load condition is significant, comparing with the switching frequency reduction techniques. Comparing with two techniques shows that both of the techniques improve the part and light load efficiency, but reduction of frequency has a negative effect on ripple of the input inductors, current of input inductors, and also core losses. Cycle skipping modulation improves the light load efficiency without increasing the core losses. Also, the other problem is with related to EMI filtering problems by implementation of frequency reduction. But overall study shows that the cycle skipping modulation is recommended in practice. The other approach to design, to improve the efficiency of the converter is designing the turn component of the converter. Here, turns ratio of transformer is selected as a parameter to improve the efficiency of the converter. First, we should know how can turns ratio affect on the efficiency of the converter. Actually, the turns ratio affect on operation mode of the converter for special value of the input voltage. As performance of the converter is different for boost and buck mode, then we can conclude the turns ratio, the efficiency of the converter and power losses will be different for a different value of the turns ratio. As example, by selecting the input voltage range between 28 to 38, as can be seen for 3 different turns ratio. For turns ratio of 6.1, here the operation mode between boost and buck is divided equally. But regarding the turns ratio of 5.7, the operation mode of boost is wider than buck, and for turns ratio of 6.7, it's inverse, and converter operates in buck mode for input voltage more than 30 volts. 30 volts. That shows that the selecting of turns ratio effect on operation mode of the converter. Now, by analyzing the power losses and of the converter, we can know how the operation mode effect on power losses. Here, for a special value of input voltage 33 volt, we select 3 different turns ratio: 5.7, 6.1, and 6.7. As can be seen, for turns ratio of 5.7, the converter operates in boost mode. We have switching losses because in boost mode, the switching is hard, and also transformer losses dominate the other losses. But for 6.1, the converter operates in pass-through or normal mode, and we don't have switching losses because we have operation of a series resonance converter, and switching is soft. But we have power losses in transformer. In buck mode, we have switching losses and also transformer losses. But losses of transformer is high because duration of the active states is small for buck mode, and RMS current is high, and it result in high conduction losses and winding losses in transformer. But then we can see how the turns ratio of the transformer effect on operation mode and finally on power losses and efficiency of the converter. The prototype converter was tested in laboratory for given parameters. The results shows that we have a high efficiency for operation in pass-through mode for turns ratio of 6.1. But the problem is we cannot limit the operation of the converter for one point, for one spatial value of the voltage. Then comparing with boost and buck mode, the boost mode gives results low power losses and high efficiency rather than buck mode, and it could be selected as operation mode. Finally, we have some conclusions regarding given analysis. Between cycle skipping and frequency reduction techniques, in practice, the experimental shows that cycle skipping is recommended. Also, evaluation of efficiency for power loss analysis of the converter shows that highest efficiency is achieved in pass-through operating point, and also boost mode is superior to that in buck mode. The other parameters is sec efficiency of the converter that shows that for turns ratio of the 5.7 and 6.1, the converter the highest weighted efficiency. Considering overall efficiency of the converter and weighted efficiency and compatibility of the converter with the PV modules, the turns ratio of 6.1 will be the best selection. It was my presentation about the efficiency improvement techniques. I didn't go in detail. For more and further reading, you can see our papers in this topic. And this is the end of my presentation. Thank you for your attention. Okay, now it's time to go to dear Minh-Khai and his presentation about Z-source inverter. Dear Minh-Khai, floor is yours. Please start.
Hello.
Hello?
Can you see my screen? My sharing screen?
Yes, yes, yes.
Okay, thank you. Sorry. Okay, hello everybody. I'm very glad to be here to share my knowledge about impedance-source converter. Today, I will present several attractive topology. Here in my presentation outline, the first I have looked introduction about some basis impedance-source converter, and then several passive impedance source and active impedance source inverter will be present. Next, I will present several three-level impedance source inverter. In this session, I will present one of our features in the fault tolerance control for the three-level impedance source network. And the final, some conclusion, current work, and the future trends will present. Introduction. Here is the impedance source converter is very well known for all of you. So I don't want to talk more about this, but several event filter we can see here. That's the topology had a simple topology with the boost voltage in the one state power conversion. Especially it have the shoot-through immunity. The shoot-through state does mean when the post switch in the one inverter leg turn on at the same time. So that's the shoot-through duties ratio here. And we can see the boost factor, the DC voltage will be higher than the input voltage when we increase the shoot-through duty cycle. Since 2002, first proposed by Professor Peng Zhangpeng, till now we have many impedance source converter have been reported in the literature. I can classify into two groups. The first one that is the passive network, and the second one that's in the active network. Now I go to the Babaei network for impedance-source converter. So in 2008, two versions of the original topology have been modified. We can see in this figure show the ambit time and the second one that is the ceiling time. The ambit time have the advantage with the continuous input current and the low voltage rating. However, this topology you show inductor and the capacitor show the size and the weight high. And this topology, I think, when work with the high voltage gain, the conduction loss will be increased. That's it because in the shoot-through state, when we need the high shoot-through duty ratio to get the high voltage gain, the shoot-through state here, the shoot-through current, the shoot-through current equal the total two inductor current, that is the two input current. So that's why the conduction loss in this topology is so large. So to increase the voltage gain, several solution we can modify the modulation, the Peter plane control technique, and the other we can modify the topology by adding the Babaei element like inductor, capacitor, couple inductor or transformer. Here in the two topology, we can see the switch inductor add to the impedance-source network, or the couple inductor add to here. So for the couple inductor, we have several type of the couple inductor have three parts like trend source, TZ source, Y source, gamma, delta source, so many. Of course, when we add more Babaei element, this will introduce the increase the size and the weight of the power converter. And for the couple inductor in the transformer, the linkage inductor should be pay attention because it generates the spike. Now I move to the active impedance-source inverter, and one of the another name that's the quasi switch push inverter. So this topology, the first presenter had talked so much, so I will add a little bit presenting here. So here is the two versions of the quasi switch push inverter, similar to the Babaei Z-source inverter. So for the quasi switch push, we also have the two versions. The first one that is the ambit time, and the second one is the ceiling time. The ambit time had a continuous input current, while the ceiling time had a low voltage rating on the capacitor. So compared to the quasi Z-source inverter, so this topology can reduce one inductor and one capacitor, but it adds one more switch and one more diode. And especially in this topology, the shoot-through state, during the shoot-through state, the shoot-through current right now equal the input current. That's lower than the quasi Z-source inverter. In the quasi Z-source inverter, that's in the double the input current. So the conduction loss in this topology will lower than the quasi Z-source inverter, especially in the high voltage gain. And it had the same filter with the quasi Z-source inverter and the same boost factor. And again, for improved the performance of the quasi switch boost inverter, in here we can add one capacitor and one inductor back here, and we can see if the switch, the additional switch in here is turned off, and this topology back to the conventional quasi Z-source inverter. So I can call this topology that's in the active quasi Z-source inverter, because we have one more additional switch here. So we can see in this topology, not only through duty cycle control the boost factor, but also the additional duty cycle of the additional switch also contribute for the boost factor. So in this topology, by adding more boost, more duty cycle on this switch, so the through duty cycle we can minimize, and that means we can increase the modulation index. So this is suitable for the wide voltage range operation. Similar to the passive Z-source inverter. So for the active Z-source inverter, if we want to get the high voltage gain, so several passive elements like inductor, capacitor, the couple inductor add to the network. And again, this will increase the size, the weight, and the voltage spike will introduce with the couple inductor. Here is the comparison between two networks. The passive quasi Z-source and the active quasi Z-source. We can see in the passive network, the passive element, there are many elements in the passive, while in the active had several. But in the active, we add the additional switch. And because adding additional switch, we have two control parameters for the boost factor. And because the modulation is limited by this equation, so we try to keep the shoot-through as low as possible. To do that, the modulation depth is high. And then we can increase the boost duty cycle in here. That is different from the passive Z-source inverter. We just only have the shoot-through duty cycle here, and most of boost factor depend on the shoot-through duty ratio here. And when the high voltage boost so the modulation that's reduced. And as a result, the active quasi Z-source inverter had a lower conduction loss than the passive quasi Z-source inverter. Now I move to the three-level impedance-source inverter. So in 2009, several three-level impedance-source inverter introduced. So it had the boost voltage in the single-stage power conversion with the shoot-through immunity. However, because this topology based on the original Z-source network, so it have discontinuous input current, have used the two voltage source, and had the high capacitor voltage strength. Another topology that is using the quasi Z-source. In the quasi Z-source, so we can get the continuous input current and have the low voltage rating. And for the tree level, we have three methods to generate the shoot-through state. The first one, that's in the upper shoot-through. In the upper shoot-through, we can turn on the switch here to make the P node and O node connect together. And in the lower shoot-through, that means we can turn on in this way to make the O node and N node connect. And the last one, that's the full shoot-through. In the full shoot-through, on-off switch in this leg, it turn on, and the P node and the N node it connect together. By remove the inductor here and replace by the diode, so the topology has increased the voltage gain, the push factor increase. However, the input currents in the topology is discontinuous. So other topology to maintain the high voltage gain look like this. It's based on the switch capacitor network. You can see here for the tree-level version, it's used two capacitor, two diode, one switch, and one inductor to generate the tree-level with the high voltage gain, because the DC voltage now equal the total of the capacitor voltage. And the capacitor C1 and C2 have the same balance, because during the shoot-through state, the capacitor C1 and C2 are equal. And especially this topology had the zero voltage switching in the additional switch, the known here. The final topology I want to introduce here, that's in the tree-level quasi switch push inverter. So in this topology attract me because if we connect the diode D2 and D3 here, if we solve D2 and D3, this topology, it becomes the conventional two-level, conventional two-state three-level converter. And because it's based on the three-level DC-DC push converter, so the current ripple of the input inductor here is very slow because it can operate with the interlink. And again, to reduce the shoot-through state, so we can get the higher push in the T1 and T2 duty ratio. And then we can reduce the shoot-through duty cycle and increase the modulation depth in the topology. And we can more easier to get the capacitor voltage balance, because not only T1, T2 control the balance voltage, but also the shoot-through state, the upper shoot-through and the lower shoot-through can control the balance capacitor. Especially this topology has the fault tolerance filter, and here I give some example for the fault tolerance with the topology. In case of the switch S1, at the open circuit power. So during this, we can turn on switch F2A, and then the phase A connect to the neutral point. When the phase A is found, the amplitude of the output voltage is reduced compared to in the normal case. So we need to increase the duty cycle and the true duty cycle and the duty cycle of the additional switch to compensate the reduced the magnitude of the voltage because the phase A right now is disconnected. So here is the some results before loss, the capacitor here, but after loss, the capacitor we can push the higher value and to keep the current in the normal state. The second case, that is when the F2A had the open circuit power. So in that case, the phase A cannot connect to the neutral point, and the phase A operates with the 2 level, while the phase B and phase C still keep the 3 level. And in this case, the harmonics of the phase A is increased, but we can keep the output value is stable with the before the fault. And the last case, that's the fault open circuit fault in the T1 or the T2. This filter cannot fall in the 3-level push DC-DC converter, because in the 3-level push DC-DC converter, when the one of the switch in here fault, the network cannot operate. But in this topology, it still works. And how it works? So we can see in this figure when the switch T1 had the open circuit power, and we can turn on the S1 and S2, turn on here to make the P node and the O node connect together. And right now, the inverter side had the DC-link, the new DC-link voltage, that is the O and N. And the O and N right now that's equal the VC2. And the converter operate with the 2-level even. And here is the 2 state of the T2 on and T2 off. So to compensate the voltage reduction from the DC-link. So the T2 by control the duty ratio of the T2, so we can increase the voltage of the capacitor C2. Here we can see the results show that after fault, so the capacitor C2 had to boost the voltage to keep the DC-link voltage in high to get the current, the output current back to the normal case. So for more detail, so you can find in this in our publication. So here is the summarize of the 3-level Z-source inverter. With the bus C network, we can see there are many of the bus C element, while the active network has a lower bus C element, but the semiconductor is increased in the active network. And because the additional switch, so we have flexible control for the voltage gain for the push factor. And then the voltage balance that's be more easier than the other topology. For example, if we need the balance control of the two capacitor, the capacitor voltage, so we need to sense more voltage. So now I conclude my presentation and show some current works and the trends, the future trends for the impedance source network. Although many impedance source network have introduced, but we still need the new impedance source network for different applications. For example, in the multi-level inverter, for the wireless power transfer, and for the DC-DC converter with the isolate, with the wide voltage range operation. We still need the new modulation technique, the space vector modulation and the range control methods to reduce the common mode voltage, improve voltage gain, and improve the efficiency, and especially the reliability, because this topology had the shoot-through immunity. So we should more investigate on the reliability, for example, in the fault tolerance control, in the EMI noise, and of course the wide bandgap device that is still the new direction for the impedance source network. And thank you for your time. Thank you very much.
Thank you for your nice presentation, dear Minh-Khai. And now it's time to have discussion and question. Please don't be shy and ask if there is questions. We are here. Any question?
Can you hear me?
Yes, please.
Yeah. You discuss about regarding that efficiency improvements. Can
Okay.
you, for impedance source networks, can we switching techniques for improving that efficiency?
Could you please repeat?
Soft switching techniques for improving the efficiency of that impedance source network. Can you go that one?
From which presentation?
From yours only. You told that for improving that efficiency, you are reducing
Yes.
the switching frequency. You are reducing. Okay.
Yes.
Yeah. If you use that impedance soft switching techniques, you
Yes.
can go for a higher switching frequencies. Then transformer size and inductor size and capacitor size can be reduced. Then the system will be compact in size.
Yes.
Okay.
Yes.
Can we go for that one impedance soft switching techniques for that one?
Impedance source technique.
No, soft switching techniques for impedance source network.
Soft switching is done by series resonance tank. Yes.
Okay, actually, one more question I have to ask. In the literature, I found that when we are using that, when we are designing that coupled inductor type of networks, there will be leakage inductors are there. Okay. Because of that leakage inductance, that in front side some diodes will be there in the impedance source network. Suppose in Y source network, one diode is there initially. During the shoot through, the diode has to reverse bias. Okay. Because of one more thing. Because of leakage induction, that diode was continuously conducting. If it is continuously conducting, what will happen? What is the reason? What will happen?
But we don't use diode and impedance source network. We use a synchronous switch to prevent this discontinuous current from there.
Okay.
Mhm.
That's. Can you go for soft switching techniques for improving that efficiency?
I don't understand what you mean.
Okay. Once again, I will repeat that question. Actually, for impedance source network, for improving that efficiency, you told that switching frequencies a lower value are going there. Frequency is a lower value.
Okay.
If I use soft switching techniques, I can we can go for higher frequencies.
Okay, but we use it only for how to say in light load conditions. We control the system for light load conditions. When the system works in light load condition, we use these techniques for decrease the switching losses.
Okay. Okay, sir. Thank you.
Okay, the other question, if okay, from Abul Qasim. Could you please, Qasim, say me, you asked a question from me or?
For the inverter presentation, last presentation.
From Minh-Khai.
Yeah.
Dear Minh-Khai, Qasim have a question. He asked, how could the conflict between the duty cycle value and the modulation index be avoided in the closed loop system in case of inverter?
So you mean we had two control parameters.
Yeah.
First one is
Shoot through.
Yeah, and the second one is the additional switch duty ratio, right?
Yeah. It's the conflict between the value of shot to throw and the modulation index for the closed loop system. Is there any limitation in the design or something?
Yeah. That's the trade-off balance between two parameters. We need to optimize the selection. We have the first priority that we get the low shoot-through duty ratio first, and to do that, so we need to control the additional switch duty ratio first, and when the additional switch limit until the value, so this value you can define based on the analysis with adding the parasitic consideration, and then you can find out the good point for operation with the maximum duty ratio, and then if we need more voltage gain, so in that time we switch the shoot-through duty ratio.
Okay, thank you.
Yeah.
Thank you for your question, and also thank you for answer, dear Minh-Khai. Another question. There is question. No. Okay, I think there is no other question. Then we can finish our webinar. At the end, I would like to thank dear Ebrahim, dear Sertac, and dear Minh-Khai for nice presentation, and also for your kindness in participation in this webinar. I hope to see each other in real condition, not virtually, and I hope to be safe. Thank you very much for your attention and participation. Thank you.
Thank you. Thank you for
Thank you all.
the
Have a nice
invitation
day.
to listen this
Thank you
webinar.
for
Hope
next
to see all of you in the personal.
Thank you. Bye.
Bye-bye.
Bye.
Thank you, everybody. Bye bye.
Thank you.